Hello dear students, today we are discussing section 1.4, that is quotient normed space. We have already defined about what is quotient normed space. So in this section we are concentrating on the norm of cos set x, that is, let us call it as quotient norm. Quotient norm on x, that is quotient norm on the space x quotient x naught, where x is a linear space and x naught is the subspace of capital X. And we have to show that this norm is a norm, that is, it satisfies all the conditions required, or the three conditions required for a norm, which is defined by infimum of small y belongs to capital X naught, norm of x minus y, where coset of x belongs to x coset x naught. Let us recall that x coset x is the values such that x plus x naught, where x naught is a linear space of capital X. Let us recall one more thing, that is the conditions required for a norm is: first one, norm x greater than or equal to 0. Second one, the sub condition is norm x equal to 0 if and only if x equal to 0. The second condition is norm of lambda x equal to mod lambda into norm x. Third condition is norm of x plus y less than or equal to norm x plus norm y. So let us enter into the proof. That is, we have to show that this quotient norm is greater than or equal to 0 and quotient norm equal to 0 if and only if coset x equal to 0. Here our element is coset x, and the other two conditions also we have to prove they are satisfying the second and third conditions. Now let us enter into the proof. Now by definition itself, norm of coset x is the infimum of many positive values. That means norm of coset x is greater than or equal to 0. Now let norm of coset x equal to 0, which means by definition infimum y belongs to x naught, norm of x minus y equal to 0. So we are considering different values from x naught, that is, say y1, y2, y3, etc. Here infimum y belongs to x naught, norm of x minus y means we are finding many values from x naught, say x, y1, y2, etc. And we are finding norm of x minus y1, norm of x minus y2, etc. norm of x minus yn. And we are finding the infimum of such values, and it is equal to 0. Which means there should exist a sequence yn in capital X naught such that norm of x minus yn converges to 0. Which means yn converges to small x. Now yn belongs to x naught and x naught is closed, which means the limit of xn should contain in x naught, that is, x belongs to x naught. So we are considering the quotient space as x quotient x naught. Therefore x belongs to capital X naught simply means coset of x equal to 0. That is, norm of coset x equal to 0 if and only if coset of x equal to 0. So the second condition is also satisfied. Now the next condition, norm of coset lambda x. By definition of coset of lambda x is nothing but lambda into coset x. Again, by definition of norm of lambda into coset x is same as mod lambda into norm of coset x. That is, norm of coset lambda x is same as mod lambda into norm of coset x. And to prove the triangular inequality, we are considering that for every epsilon greater than 0, we can take z1, z2 belongs to capital X naught such that norm of x plus z1 is less than or equal to norm of coset x plus epsilon. By definition, norm of coset x is the infimum of many values. So infimum, a set of values. We are considering a set of values. Norm of x plus z. Z belongs to x naught. And we are considering the infimum of such values. So infimum plus epsilon means there should exist at least one element in that set such that that element is less than or equal to infimum plus epsilon. Such element, let such elements be z1 and z2. That is, norm of x plus z1 is less than or equal to norm of cosec x plus epsilon, and norm of y plus z2 less than or equal to norm of cosec y plus epsilon. It follows that for every epsilon greater than 0, we have norm of cosec of x plus cosec y is equal to infimum. Z belongs to x naught, norm of x plus y plus z. It is by definition of quotient norm. That is, norm of cosec x plus cosec y is nothing but norm of cosec of x plus y. Now by definition it is equal to infimum of z belongs to capital X naught, norm of x plus y plus z, which is less than or equal to norm of x plus y plus z1 plus z2. Again, this is the infimum. So infimum is less than or equal to any element of the set of the form x plus y plus some element. Let that element be z1 plus z2, because each z, z1, z2, etc. r belongs to x naught. And by triangular inequality of a norm, we can write like this: norm of x plus z1 plus norm of y1 plus z2, which is less than or equal to norm of cosec x plus norm of cosec y plus 2 epsilon. Now since epsilon greater than 0, we prove the triangular inequality for the quotient norm. So this is hence the proof. Now let us define what is a semi-norm. Semi-norm is a function p from e to r plus. That is, it is a positive valued function satisfying three conditions. P of 0 equal to 0, P of lambda x equal to mod lambda into P of x, P of x plus y is less than or equal to P of x plus P of I. These conditions are the conditions to be a norm. But for norm, P of x equal to 0, if and only if x equal to 0 should be there. But in the case of semi-norm, the semi-norm may vanish for non-zero elements of the space. That is, you should understand one thing, that is P of x equal to 0. In the case of semi-norm, P of x equal to 0 need not imply that x equal to 0. Usually, norm of x equal to 0 if and only if x equal to 0. But in the case of semi-norm, here we are denoting p as the function instead of norm. That is, p of x equal to 0 need not imply that x equal to 0. That is, p of 1 may be 0. That is, p of non-zero values may be 0. That is the difference between semi-norm and norm. There is only one difference. Now, if lambda, usually we are taking lambda as a real values. If lambda belongs to C, that is, if lambda is a complex value, then the space is over complex numbers. Now, kernel of, let us define the kernel of a semi-norm. Let P of x be the semi-norm on the linear space capital E. Then the kernel of the semi-norm is defined by E naught, which is equal to set of all x belongs to capital E such that P of x equal to 0. As we know about the kernel, the set of all values for the function is equal to 0. It is just the kernel. But here, if we are defining the function as semi-norm, it is the kernel of semi-norm. Now you have one assignment, that is thus to prove that E naught is a subspace. That is, you should prove that kernel is a subspace of E. By definition of subspace, you know that if you are taking any arbitrary elements of E naught, by definition of E naught, P of x equal to 0, P of y equal to 0, and you have to show that it is a subspace, means their linear combination ax plus by belongs to E naught. That is, it is enough to show that P of ax plus by belongs to E naught. Now, this is a second problem. That is, we have to prove that P of x plus y is independent of small y belongs to capital E naught, where small p is a semi-norm and E naught its kernel. P of x plus y is independent of y belongs to E naught means if we are considering any values of E naught, it is same. That is, if let us consider y1, y2, y3, y4 from E naught, then P of x plus y naught equal to P of x plus y2 equal to P of x plus y3 equal to P of x plus y4. That is, if we are varying any y belongs to E naught, P of x plus y will be same. That is meant by P of x plus y is independent of y belongs to E naught. So arbitrarily we are going to prove that P of x plus y1 equal to P of x plus y2 for any arbitrary y1, y2 belongs to E naught. For that, we are starting with P of x plus y1. And in the second step, we are adding and subtracting y2. That is P of x plus y2 minus y2 plus y1 by the triangular inequality on semi-norm. We can write like this: P which is less than or equal to P of x plus y2 plus P of y1 minus y2. Since y1 and y2 belongs to E naught and E naught is a kernel, P of y1 equal to 0, P of y2 equal to 0, that is P of y1 minus y2 is also equal to 0. That is, from first equation we get P of x1 plus y1 is less than or equal to P of x plus y2. Similarly, we can prove that P of x plus y2 is less than or equal to P of x plus y1 by from equations 1 and 2. It is clear that P of x plus y1 is equal to P of x plus y2, that is P is independent of that y. So this and y1 and y2 are two arbitrary elements. We can prove that if for any y belongs to A naught, P of x plus y is same. Now, P of quotient x is P of x and it does not depend on the representative of the quotient, which is the same meaning as P of x is P of x plus y is independent of y belongs to E naught, since quotient x is equal to x plus E naught form. Now we are defining another function. It is a space of continuous function Cp of fixed interval AB with a norm fp integral a to b modulus of f of x raised to p dx whole raised to 1 by p is less than infinity. Now this is a norm, and again, to prove that if this is a norm, we have to show that it satisfies all the three conditions. But this is actually this is not a norm, but this is a semi-norm. That is, norm P of f equal to 0 means integral a to b modulus of f of x raised to p dx equal to 0 means f of x equal to 0 almost everywhere. That is, f of x need not equal to 0 in this case. That is, this is a semi-norm. The condition for the function f to be continuous on closed interval ab is an unnecessary restriction for such a norm. That is, even if the functions are piecewise continuous on closed interval ab with finite number of discontinuities of first order which give a finite value to the Riemann integral and which are limits with respect to the norm in A is of continuous functions. Also, the space Rp of AB, that is, they are the functions in closed interval AB such that p power of their absolute value, that is modulus of f raised to p, are Riemann integrable. That is, integral a to b modulus of f raised to p should be less than infinity. This is also an example. So thank you.